Right now, as you watch this video, space itself is growing. Not slowly, not gently, but violently. Every single second, the distance between distant galaxies stretches by thousands of miles. Your brain immediately asks the obvious question, what is space expanding into? But here's what will shatter your understanding of reality. Space isn't expanding into anything. There's no cosmic warehouse waiting to be filled, no vast emptiness beyond the edge, no container holding our universe. What we're about to explore will fundamentally change how you think about existence itself. Imagine trying to find the edge of infinity. Imagine watching something create itself from pure nothingness. Imagine discovering that the most basic question about our universe, where is it expanding to, is actually impossible to answer, not because we lack knowledge, but because the question itself breaks the rules of reality. We're about to journey through the most mind-bending concepts in all of science. We'll explore invisible forces that dwarf every star combined. We'll witness the birth of space itself from quantum foam, and we'll discover why asking where the universe expands might be like asking what color Wednesday tastes like. Let's begin. Picture yourself inflating a balloon in your living room. As you pump air into it, the rubber skin stretches outward, pushing against the surrounding air. The balloon grows bigger because there's space for it to grow into. Your living room provides that space. This expansion makes perfect intuitive sense. The balloon needs somewhere to go, so it goes there. This is how every expansion works in your daily experience. Cities grow by spreading into countryside. Ice expands by pushing against water. Plants grow by extending into air. Always there's a boundary. Always there is something being pushed into. Always there is a clear distinction between what's expanding and what it's expanding into. Your brain has been trained by a lifetime of these experiences, so when cosmologists tell you the universe is expanding, you immediately picture that balloon. You imagine our cosmic space stretching outward into something. Some vast room, some infinite emptiness waiting to be filled. But the universe laughs at this logic. Here's where physics shatters your comfortable assumptions. Space doesn't expand into anything. There is no cosmic living room. There is no container. There is no outside for the universe to grow into. When space expands, it creates the very concept of space as it grows. Think of it this way. Imagine you're trying to draw a circle bigger than your piece of paper. Instead of getting a larger piece of paper, the paper itself grows to accommodate your circle. But that's not quite right either, because in that analogy, there's still you, standing outside the paper, watching it grow. In reality, you are the paper. You are part of the drawing. You are inside the very thing that's expanding, and there is no outside perspective from which to watch it happen. Scientists discovered this mind-bending truth by becoming cosmic detectives, following clues written in the light of distant stars. In the 1920s, Edwin Hubble pointed the world's largest telescope at spiral-shaped clouds in the night sky, trying to answer a simple question. Were these clouds part of our galaxy or something else entirely? What he found was revolutionary. These weren't clouds at all. They were entire galaxies, each containing hundreds of billions of stars, sitting millions of light years away from our Milky Way. In an instant, the known universe expanded from one galaxy to countless billions. But that wasn't the discovery that changed everything. As Hubble measured the distances to these galaxies, he noticed something impossible. Every single galaxy was moving away from us. Not just a few, not just the distant ones. Every galaxy he could observe showed red-shifted light, the telltale signature of objects receding at tremendous speeds. Even more bizarre, the farther away a galaxy was, the faster it appeared to be fleeing. Galaxies twice as distant moved away twice as quickly. Galaxies 3 times farther moved 3 times faster. This pattern suggested we were sitting at the center of a cosmic explosion, with everything else racing away from us through space. But this created an impossible problem. If we were at the center of this explosion, it would mean Earth occupies a special, privileged position in the cosmos. This violated everything we'd learned since Copernicus, that we are not the center of anything. The solution was even more mind-bending than the problem. Imagine dots painted on the surface of a balloon. Now imagine inflating that balloon. As the rubber surface expands, every dot sees every other dot moving away. The farther apart two dots are, the faster they separate. Yet no dot is special. No dot sits at the center of expansion. Each dot experiences exactly what Hubble observed. Everything else moving away, with distant objects receding at faster. Replace the balloon surface with the three-dimensional space you live in, and you have cosmic expansion. The galaxies aren't racing through space like debris from an explosion. Space itself is stretching, carrying the galaxies along like raisins in rising bread dough. This means when you ask what the universe is expanding into, you're asking what the dough is expanding into. But you are part of the dough.
How can we be certain this bizarre process is actually happening? The answer lies in watching light itself get tortured by expanding space as it travels across the cosmos. When a distant galaxy fires a beam of light toward Earth, that light begins its journey with a specific wavelength. Blue light, red light, infrared. Each wavelength carries a signature like a cosmic fingerprint, telling us about the elements and processes in that distant galaxy. But as the light travels through expanding space, something extraordinary happens. The space the light moves through grows larger during its journey. Imagine you're walking across a moving walkway that's slowly stretching as you walk. Your steps stay the same size, but the ground beneath you keeps growing longer. By the time you reach the end, you've traveled much farther than your steps should have taken you. Light experiences something similar, but instead of traveling farther, its wavelength gets stretched. Blue light from a distant galaxy arrives at our telescopes as red light, not because the galaxy moved away like a speeding ambulance changing its siren pitch. The light gets redder because space itself expanded during the light's billion-year journey to reach us. Here's a number that will rewire your brain. Light from the most distant observable galaxies has been stretched to nearly 40 times its original wavelength. What started as intense ultraviolet radiation now reaches us as faint infrared heat. This means the universe expanded by a factor of 40 during that light's journey. Think about this carefully. The galaxy that sent you this ancient light looks tiny and faint in our most powerful telescopes. But when that light first departed, the universe was 40 times smaller than it is today. That galaxy was much closer to where our Milky Way would eventually form. But here's what makes this even more mind-bending. This stretching isn't happening somewhere else, it's happening everywhere, right now. The space in the room where you're watching this video is trying to expand. The space between your eyes and your screen wants to grow larger. The only reason you don't notice this expansion is that electromagnetic forces between atoms are far stronger than the expansion rate. Only across vast cosmic distances, where there are no atomic forces to resist it, does this expansion become noticeable.
We live inside the ultimate cosmic prison, and the walls are made of time itself. When you look up at the night sky, you feel like you're seeing the universe, the whole thing, all of reality stretched out above you. But here's the truth that will reshape how you think about existence. You're seeing less than 4% of what's actually out there. You're trapped inside an invisible sphere with a radius of about 46 billion light years. Beyond this boundary lies more universe, billions more galaxies, trillions more stars, perhaps even other versions of you experiencing the same realization. But you will never see any of it. Not with any telescope humanity could ever build, not with any technology that could ever exist. The trap isn't made of walls or barriers. It's made of the finite speed of light combined with the finite age of the universe. Light takes time to travel. When you look at the sun, you see it as it was 8 minutes ago. When you look at the nearest star, you see it as it was 4 years ago. Look at the Andromeda galaxy, and you're seeing 2.5 million years into the past.
The farther you look into space, the deeper you peer into history. Here's where the trap closes around you. The universe is 13.8 billion years old. This means the oldest light that could possibly reach you has been traveling for 13.8 billion years. Any galaxy farther than this distance might as well not exist from your perspective. Its light simply hasn't had enough time to reach you yet. But expansion makes the trap even more confining. That distant galaxy was much closer to us when it emitted the light we see today. By the time its ancient light reaches our telescopes, expansion has carried that galaxy far beyond the original 13.8 billion light-year mark. Today, that galaxy sits about 46 billion light-years away. This creates your cosmic prison cell. Everything beyond 46 billion light-years exists in what scientists call the unobservable universe. You cannot see it, you cannot detect it, you cannot prove it exists. Yet logic and mathematics tell us it must be there. If the universe is infinite, then your observable bubble contains exactly 0% of what actually exists. 0%. The most ancient light in the universe is screaming toward you right now at 600 million miles per hour, carrying a message from the moment reality began. This light has been traveling longer than Earth has existed, longer than our solar system formed, longer than our galaxy took its current shape. It began its journey when the universe was only 380,000 years old, back when the cosmos was a seething mass of plasma so hot that atoms couldn't even form. We call this ancient radiation the cosmic microwave background, and it's everywhere. Turn on an old television between channels, and about 1% of that static comes from this primordial light. You're literally seeing the afterglow of creation flickering across your screen. But here is what makes this discovery so profound. This light represents the edge of everything we can observe. Before that moment, 380,000 years after the Big Bang, the universe was opaque. Imagine trying to see through the surface of the sun. The early universe was like that everywhere, a thick fog of plasma that blocked all light. Then, something miraculous happened. The expanding universe cooled enough for protons and electrons to combine into the first hydrogen atoms. Suddenly, the cosmic fog lifted. The universe became transparent. Light could finally travel freely across space. The first photons that escaped this cosmic clearing are the ones reaching your eyes today as the microwave background. This moment, called recombination, created the ultimate horizon. You cannot see past it ever. Any events that happened in those first 380,000 years remain forever hidden. This cosmic microwave background shows us the universe when it was smoother than a perfectly polished mirror, with only tiny temperature variations of a few millionths of a degree. Those microscopic temperature differences would eventually become everything. Every galaxy, every star, every planet, every life form that has ever existed.
The cosmic microwave background revealed something that should have been impossible. The early universe was incredibly smooth, almost perfectly uniform. But this uniformity creates a devastating problem for our understanding of cosmic evolution. Different regions of the observable universe are separated by such vast distances that light could never have traveled between them, even in the entire age of the universe. These regions have been causally disconnected since the beginning of time. They could never have communicated. They could never have reached the same temperature. Yet they're all at exactly the same temperature. It's like finding that the temperature in your house perfectly matches the temperature in a house on the other side of the galaxy, even though no heat sources ever connected the two locations. This shouldn't be possible. The solution involves the most violent event in cosmic history, a period of expansion so rapid and extreme that it defies every intuition you have about how the universe works. During the first tiny fraction of a second after the Big Bang, a period so brief that light could travel less than the width of a proton, the universe expanded more than it has in all of the 13.8 billion years since. This period, called cosmic inflation, stretched space so violently that regions of the universe lost contact with each other forever. Points that were once close enough for light signals to travel between them were suddenly separated by distances that light could never cross. Here's the number that will break your brain. Inflation increased the size of the universe by a factor of at least 10 to the 26th. That's like a grain of sand suddenly becoming larger than the observable universe today. This expansion happened in about 10 to the minus 35th seconds. To put this timescale in perspective, light travels about 1 foot in a nanosecond. During inflation, the universe expanded by more than 20 orders of magnitude in a time so short that light could barely cross the width of a subatomic particle. The energy driving this expansion came from quantum fields stuck in high-energy states called false vacuums. While trapped in these states, these fields created a temporary form of dark energy far more powerful than anything we observe today. During inflation, space doubled in size, then doubled again, over and over, every infinitesimal instant. This exponential growth solved the smoothness problem by taking a tiny region that could reach uniform temperature and stretching it to cosmic scales. But inflation did something even more remarkable. It took quantum fluctuations, random uncertainty at the subatomic level, and stretched them to cosmic scales. These microscopic variations in energy density became the seeds that eventually grew into galaxies, stars, and planets. Every structure in the universe, including you, traces back to quantum uncertainty amplified by inflation.
The most ancient light in the universe is screaming toward you right now at 600 million miles per hour, carrying a message from the moment reality began. This flight has been traveling longer than Earth has existed, longer than our solar system formed, longer than our galaxy took its current shape. It began its journey when the universe was only 380,000 years old, back when the cosmos was a seething mass of plasma so hot that atoms couldn't even form. We call this ancient radiation the cosmic microwave background, and it's everywhere. Turn on an old television between channels, and about 1% of that static comes from this primordial light. You're literally seeing the afterglow of creation flickering across your screen. But here's what makes this discovery so profound. This light represents the edge of everything we can observe. Before that moment, 380,000 years after the Big Bang, the universe was opaque. Imagine trying to see through the surface of the sun. The early universe was like that everywhere, a thick fog of plasma that blocked all light. Then something miraculous happened. The expanding universe cooled enough for protons and electrons to combine into the first hydrogen atoms. Suddenly, the cosmic fog lifted. The universe became transparent. Light could finally travel freely across space. The first photons that escaped this cosmic clearing are the ones reaching your eyes today as the cosmic microwave background. This moment, called recombination, created the ultimate horizon. You cannot see past it ever. Any events that happened in those first 380,000 years remain forever hidden. The cosmic microwave background shows us the universe when it was smoother than a perfectly polished mirror, with only tiny temperature variations of a few millionths of a degree. Those microscopic temperature differences would eventually become everything. Every galaxy, every star, every planet, every life form that has ever existed. The cosmic microwave background revealed something that should have been impossible. The early universe was incredibly smooth, almost perfectly uniform. But this uniformity creates a devastating problem for our understanding of cosmic evolution. Different regions of the observable universe are separated by such vast distances that light could never have traveled between them. Even in the entire age of the universe, these regions have been causally disconnected since the beginning of time. They could never have communicated. They could never have reached the same temperature. Yet they're all at exactly the same temperature. It's like finding that the temperature in your house perfectly matches the temperature in a house on the other side of the galaxy, even though no heat source has ever connected the two locations. This shouldn't be possible. The solution involves the most violent event in cosmic history, a period of expansion so rapid and extreme that it defies every intuition you have about how the universe works. During the first tiny fraction of a second after the Big Bang, a period so brief that light could travel less than the width of a proton, the universe expanded more than it has in all the 13.8 billion years since. This period, called cosmic inflation, stretched space so violently that regions of the universe lost contact with each other forever. Points that were once close enough for light signals to travel between them were suddenly separated by distances that light could never cross. Here's the number that will break your brain. Inflation increased the size of the universe by a factor of at least 10 to the 26th. That's like a grain of sand suddenly becoming larger than the observable universe today. This expansion happened in about 10 to the minus 35 seconds. To put this timescale in perspective, light travels about 1 foot in a nanosecond. During inflation, the universe expanded by more than 20 orders of magnitude in a time so short that light could barely cross the width of a subatomic particle. The energy driving this expansion came from quantum fields stuck in high-energy states called false vacuums. While trapped in these states, these fields created a temporary form of dark energy far more powerful than anything we observe today. During inflation, space doubled in size, then doubled again, over and over, every infinitesimal instant. This exponential growth solved the smoothness problem by taking a tiny region that could reach uniform temperature and stretching it to cosmic scales. But inflation did something even more remarkable. It took quantum fluctuations, random uncertainty at the subatomic level, and stretched them to cosmic scales. These microscopic variations in energy density became the seeds that eventually grew into galaxies, stars, planets, every structure in the universe, including you, traced back to quantum uncertainty amplified by inflation.
For decades after discovering cosmic expansion, astronomers assumed gravity would eventually win. All that matter scattered throughout space should act like a cosmic brake, gradually slowing expansion until everything either stops growing apart or begins collapsing back together. In 1998, 2 teams of scientists set out to measure exactly how much expansion was slowing down. Instead, they discovered something impossible. Expansion is speeding up. Using exploding stars called Type A supernovae as cosmic lighthouses, they found that distant supernovae were fainter than expected. This meant they were farther away than standard expansion models predicted. Somehow, space had grown more than it should have during the light's journey to Earth. The only explanation was that expansion itself was accelerating. Something was pushing space apart with increasing strength. Scientists call this mysterious force dark energy, and it dominates everything. Dark energy makes up roughly 68% of the total mass energy content of the universe. It outweighs all ordinary matter by more than 13 to 1. Yet we have no idea what it is. Here's what makes dark energy so weird. It doesn't dilute as space expands. Normal matter becomes less dense as the universe grows. Spread a fixed amount of matter across twice as much space, and you get half the density. But dark energy maintains constant density even as space grows. As the universe expands, new dark energy appears to fill the additional volume. This means dark energy's total influence grows over time. In the early universe, when everything was compressed together, matter dominated cosmic evolution. But about 5 billion years ago, roughly when our solar system formed, dark energy became the dominant force. We live in the age of acceleration. Every day, dark energy becomes more influential. Every day, expansion accelerates a bit more. The universe manufactures new space from pure nothingness at a rate that would make every factory on Earth weep with envy. Every second, the volume of observable space increases by roughly 10 to the 78 cubic meters. That's a number so massive that if you tried to count that high, one number per second, you'd need more time than the universe has existed multiplied by itself billions of times. All this new space emerges from what physicists call the quantum vacuum. But the quantum vacuum isn't the empty void you might imagine. It's a seething foam of virtual particles popping into existence and annihilating each other in time frames shorter than the smallest measurable instant. According to quantum mechanics, even in the most perfect vacuum, energy fluctuations continue.
particle-antiparticle pairs flash into existence, borrow energy from the vacuum, and destroy each other before the universe notices the energy debt. This process fills every point in space with activity. Here's the mind-bending part. This vacuum energy has gravitational effects, but unlike matter, which pulls things together, vacuum energy creates repulsive gravity. It pushes space apart. The more space you have, the more vacuum energy you get. The more vacuum energy you get, the more space expands. The more space expands, the more room there is for new vacuum energy. This creates a runaway process. During the universe's first fraction of a second, this process ran wild during inflation. Today, a gentler version continues as dark energy drives ongoing acceleration. String theory, our most ambitious attempt to unify all physics, suggests that space might have more dimensions than the 3 you can move through. If string theory is correct, space actually has 9 dimensions, with 6 additional dimensions curled up so tightly that even particles cannot detect them. Imagine you're an ant walking on a garden hose. From your perspective, you can move forward or backward along the hose, experiencing what seems like one-dimensional space. But the hose actually has 3 dimensions. The circular dimensions around the hose are so small compared to your size that you cannot perceive them. We might be like that ant, aware of only 3 spatial dimensions, while 6 others remain curled up beyond our perception. If these extra dimensions exist, they could provide the answer to what the universe expands into. Our familiar 3-dimensional space might be expanding into higher dimensional space that contains it, like a balloon surface expanding in 3-dimensional air. This concept, called the Brand-World model, suggests our entire universe is a 3-dimensional membrane floating in 9-dimensional hyperspace. Everything we can observe might be confined to this membrane, while space expands within the larger hyperspace. But here's what makes this possibility truly mind-bending. Other membranes might exist parallel to ours in the extra dimensions. These parallel universes could be separated from us by less than a millimeter in directions we cannot point to or move in. While you contemplate these words, trillions of other universes might be inflating into existence, each with different laws of physics, different constants of nature, and different possibilities for life. If inflation happened once, quantum mechanics suggests it should happen continuously throughout a larger space called the multiverse. Random quantum fluctuations can trigger new episodes of inflation anywhere, anytime. Each episode creates a bubble universe that expands and cools, potentially developing its own galaxies, stars, and planets. Our universe would be just one bubble in an infinite foam of realities. Each bubble universe might have different physical laws. The strength of gravity could be different. The mass of electrons could vary. The number of dimensions of space might not equal 3. Most of these universes would be inhabitable wastelands. In some bubbles, gravity might be so strong that stars collapse immediately into black holes. In others, gravity might be so weak that matter never clumps together to form structures. But in an infinite multiverse, even the most unlikely possibilities must occur somewhere. We exist in a habitable bubble, not because we're special, but because we can only exist in habitable bubbles.
The universe is racing toward a state so cold and empty that no process capable of generating energy will remain possible anywhere, ever. This inevitable destination, called heat death, represents the ultimate victory of cosmic expansion over every other force in nature. The timeline for this cosmic ending is almost incomprehensibly long. In about 100 billion years, the last stars will exhaust their nuclear fuel and fade to darkness. No new stars will form because expansion will have stretched matter too thin for gravity to gather new stellar nurseries. After 10 to the 34 years, even protons will decay into lighter particles, the atoms that make up your body. The atoms that form planets and stars will spontaneously disintegrate. Matter as we know it will cease to exist. After 10 to 100 years, black holes will become the only significant sources of energy in the cosmos. When the last black hole finally evaporates through Hawking radiation, the universe will achieve perfect heat death. No temperature differences will exist anywhere, no chemical reactions will be possible, no life of any kind can survive. But expansion creates an even more immediate threat. As space stretches faster, distant galaxies disappear from our observable universe. In about 150 billion years, only our local group of galaxies will remain visible. Future astronomers will observe a universe that appears to contain only a few dozen galaxies surrounded by empty space. These future scientists will see no evidence of cosmic expansion because all the expanding regions will lie beyond their observational horizon. The cosmic microwave background will also disappear, redshifted to undetectable wavelengths. Future civilizations will lose the very evidence that allowed us to understand cosmic origins. But heat death might be the gentler option. If dark energy continues strengthening, expansion might accelerate so violently that it eventually overcomes every force holding matter together. In about 22 billion years, dark energy might become so powerful that it tears apart every atom in the universe, shredding reality itself down to its fundamental components. This catastrophic end, called the Big Rip, would unfold according to a terrifying timeline. About 1 billion years before the Big Rip, expansion becomes strong enough to overcome gravity on galactic scales. Galaxy clusters dissolve, individual galaxies drift apart into the growing void. 200 million years before the end, expansion tears apart individual galaxies. Stars get ripped away from their galactic homes and scattered across space. 30 minutes before the Big Rip, expansion overcomes the gravitational binding of solar systems. Earth gets torn away from the sun. Every planet suddenly finds itself alone in expanding space. 90 seconds before the end, expansion becomes strong enough to overcome molecular bonds. Atmospheres disperse into space. Oceans boil away as the space between water molecules expands faster than intramolecular forces can maintain liquid cohesion. 10 to the minus 12 seconds before the Big Rip, atomic nuclei disintegrate. The strong nuclear force finally succumbs to the relentless stretching of space. Every atomic nucleus in the universe spontaneously breaks apart. At the moment of the Big Rip, even space and time themselves might disintegrate.
Throughout this journey, we've been trying to answer a question that seemed perfectly reasonable. What is the universe expanding into? But now we can see why this question is fundamentally impossible to answer. It's not because we lack knowledge or better telescopes. It's because the question itself assumes something that cannot exist. When you ask what the universe expands into, you're assuming there's a pre-existing space for it to expand into. You're imagining some cosmic arena that contains our expanding universe. But the universe is not contained by anything. It is space itself. The question is like asking what's north of the North Pole. The North Pole is defined as the northernmost point on Earth. By definition, nothing can be north of it. Similarly, the universe is defined as everything that exists. By definition, nothing can exist outside it for it to expand into. The universe doesn't expand into anything because it creates the very concept of anything as it expands. There is no external arena because the universe defines what external means. This isn't a limitation of human language or scientific imagination. It's a fundamental feature of reality. Before expansion, the concepts of into and outside don't exist. Expansion doesn't just create more space, it creates the logical framework that makes spatial relationships meaningful. The universe expands by becoming more universe, not by growing into non-universe. Every cubic inch of new space that comes into being creates new possibilities for matter, energy, structure, and complexity. This realization transforms our understanding of cosmic expansion from a mechanical process to something far more profound. The universe isn't just getting bigger, it's reality bootstrapping itself into existence. We are not passengers on a cosmic vehicle traveling towards some destination. We are part of the process by which reality creates itself. Our consciousness, our questions, our desperate need to understand what the universe expands into are all expressions of the universe coming to know itself. The expansion we observe isn't separate from us. We are expansion. We are space and time and matter and energy organizing themselves into patterns complex enough to ask questions about their own existence. Time itself stretches along with space, and this changes everything about how the universe ages. As cosmic expansion pulls space apart, it also stretches the flow of time throughout the universe. Events in distant galaxies appear to unfold in slow motion compared to events happening nearby. A supernova explosion that takes 3 weeks to brighten and fade in a nearby galaxy takes much longer when observed in a distant, rapidly receding galaxy. Light from galaxies at the edge of our observable universe is redshifted by a factor of about 10, meaning events in those galaxies appear to unfold 10 times slower than events happening here. This creates a bizarre situation where the age of the universe depends on your location. The early universe didn't just contain more compressed space, it contained more compressed time. Processes that take billions of years today happened much faster in the dense early cosmos. At the smallest scales of reality, space itself bubbles with virtual particles that pop into existence and annihilate each other in timeframes so brief that you could never detect them directly. Yet these phantom particles create real effects that influence everything in the universe. Imagine zooming into empty space with a microscope powerful enough to see distances smaller than an atomic nucleus. As you magnify down to the Planck scale, about 10 to the negative 35 meters, space itself becomes grainy and turbulent. At this scale, the smooth fabric of spacetime dissolves into a frothy chaos of appearing and disappearing geometry. Virtual particles borrow energy from the vacuum, and according to Heisenberg's uncertainty principle, the more energy they borrow, the faster they must pay it back. These transactions happen so quickly, they seem to violate conservation of energy, but they actually obey quantum mechanics perfectly. When physicists calculate how much energy the vacuum should contain, they get an answer 120 times larger than the dark energy we observe. This represents the most embarrassing failure in theoretical physics. Either our understanding of quantum mechanics is wrong, or some unknown mechanism cancels out most of the vacuum energy. The universe might be shaped like a donut, and expansion might be nothing more than the donut getting fatter. General relativity allows 3 possible geometries for space. Space could be flat, like an infinite sheet of paper. It could be curved, like the surface of a sphere, where parallel lines eventually meet. Or it could be curved like a saddle, where parallel lines diverge. Current observations suggest our universe is either flat or so close to flat that any curvature is undetectable. But flat doesn't necessarily mean infinite. You can roll a flat sheet of paper into a cylinder or connect its edges to make a donut shape. If space wraps around itself like a donut, then asking what it expands into becomes meaningless. A donut getting larger doesn't expand into anything, it simply becomes a bigger donut. Every thought you've ever had, every memory you formed, every piece of information that makes you who you are exists as specific arrangements of matter and energy in space. And cosmic expansion is slowly stretching those arrangements toward dissolution. This creates a fundamental paradox. Information cannot be destroyed according to quantum mechanics, yet expansion seems to disperse information across such vast distances that it becomes practically irretrievable. As space expands, the precise arrangements of molecules in your brain would eventually be separated by distances larger than galaxies. The information patterns that create your thoughts would become so dispersed that no physical process could reconstruct them. But quantum entanglement might provide a solution. The quantum states that encode information might not depend on specific spatial locations, but rather on the relationships between particles regardless of their separation. Even if expansion separates entangled particles by billions of light years, their quantum states remain correlated.
After this journey through inflation and dark energy, multiverses and quantum foam, the beginning and end of time itself, we arrive at the deepest answer to our original question. The universe doesn't expand into mystery, into wonder, into the endless capacity for more questions, more discoveries, more moments of recognition that we are part of something vastly larger than ourselves, yet intimately connected to our smallest thoughts. We are the universe asking what it expands into. We are the expansion asking where it's going. We are space and time awakening to their own existence and marveling at the infinite creativity of the process that brought us into being. The question that brought us here, what is the universe expanding into, transforms from a puzzle to be solved into a celebration of the magnificent impossibility of existence itself. The universe expands into itself, creating infinite room for infinite possibilities, including the possibility of beings like us who can stand in awe of the whole impossible, beautiful process. In asking where the universe is expanding to, we discover that we are the expansion, we are the question, and we are the answer. Conscious space contemplating its own growth, aware time pondering its own flow, organized matter marveling at its own complexity. The universe expands into the infinite potential for what can be. And right now, in this moment, as space stretches and time flows and energy organizes itself into the patterns of your consciousness, you are that potential, becoming aware of itself. This is the ultimate answer to the impossible question. The universe expands into you.